Hey, my name is Yitzhak Mandelbaum. I am the tech lead for C++ safety at Google. And I'll be talking to you today about my vision for what I call practically safe C++. This represents the work of many, mostly not myself. In particular, I just want to call out the tech leads for some of the key sub-projects here. Wante Choi, Utkarsh Saxena, and Jan Vang. Two of them actually contributed significant amounts to the slides themselves. So with that, I was here a year ago talking on the same topic, and at that point I motivated the talk and kind of the area by focusing on two key points. One is the evolving government standards in kind of software security, and the other is the competition that C++ is facing from Rust. These are still interesting motivations, they're still valid, but they feel kind of quaint, looking 1 year on. At this point, I feel like everything people can talk about now, and particularly for memory safety, is this apocalypse. I particularly like this quote from Take Shelter, which I have not seen, but I was looking for a different quote and found this one, and it was even better. So, let's just say there's a storm coming like nothing you've ever seen, and not a one of you is prepared for it. And that's the feeling I have, and I think many in the industry have, with the kind of coming wave of the expected attacks from AI. This is just kind of a sample of the headlines that I pulled when I was making the talk. Core collapse, how AI is blowing cybersecurity apart. Or Vompocalypse now. I won't read them all at you, but my favorite one I think is this one, is Are We Cooked? Because that's how I really feel. Maybe, I think we have to fight the good fight, but it's really unclear, how this story is going to go over the next few months and certainly years. And just to bring this into kind of the realm of data, this is a graph of basically the time from when a vulnerability is reported to when it's seen in the wild. And we're all familiar with the idea of 0 days, so clearly there's always been a notion where you find a vulnerability exploited before you even knew it existed, but there's long been many vulnerabilities which were first reported before they were used. And this just gone down and down and down. And so while the announcement of Project Glasswing recently from Anthropic was, I think, a milestone in this story, we've seen this coming for quite a while, as we've seen just kind of the ability of frontier models to just churn out not just vulnerabilities, but actually entire exploit chains. Okay, so this is not a security conference. Why am I sitting here at C++ now talking to you about this? That's because there's been a pretty stable statistics over the past, 2 decades that memory safety problems are basically about 70% of high severity vulnerabilities that are found. So as much as we keep working on this, we're not getting that much better, and it's a major problem. And when you talk about memory safety vulnerabilities, mostly we're looking at C and C++. Okay, so we need a safer C++. Ideally, we would have a truly memory safe C++ or some variant. And basically, I say kind of, before, to me, the story was you have this trade-off between performance and safety. You have to choose, where in the spectrum, what safety mitigations you can afford and those you can't. With the idea that people choose C and C++ because of the performance. And now, certainly for any system which faces, the internet, or a potential attacker who could get into their system, you're really talking about not really a trade-off, but system failure versus safety. And so we're looking to try and push back, improve C++. But I do want to kind of be a little conservative here and say this is a bet. There's no really, we don't know that we're going to win. If you're writing a new project, again, in one that matters because it actually can touch user data and the outside world, then I would say just writing memory safe language. Right now, C++ is not there. We're making it safer. It's not a safe language. You will have problems. Now, there's a lot of existing C++ projects. At Google, we have hundreds of millions of lines of code in C++. We can't just wave that away. And so for those, I think it really matters to invest in C++ safety. Now, most likely, being honest, I think we'll make the attacks more expensive. We'll keep amateurs at bay, but you're still going to see a significant rate of problems unless there's some magical shift from the models, doing amazing things, which everyone talks about, but we have yet to see. At the same time, this will buy us time to kind of get to memory safe languages, or maybe, again, have some breakthroughs in C++ safety. My hope is that we can get to some sort of memory safe C++ dialect. There's been a lot of talk of that over the years, so it's not like it's a new idea. We have things like Circle and Phil-C, which exist in this space, but they all kind of fall short in really giving us, I think, a practical path towards safety for the existing code bases and really being backwards compatible with all the legacy code. And so my kind of play on words here, my kind of pitch for this space is what I call practically safe C++. It's practically in the two uses of the term, almost or nearly, and kind of in a practical manner. Let's expand that. So for C++, we have, for the nearly, we have basically, not all of C++ is going to fit in memory safety. There's lots of idioms which you might know and love, and they're not going to work. We can't bring those into a space where you can be guaranteed without, say, verification and whatnot, that they are, the compiler won't be able to guarantee their safety. We're going to have to find new patterns as well that work in this model and restrict ones that have come before. We're also, I think, have to admit at the outset that not all of the code can be migrated. So for there, we get into the in a practical manner. So I'll start with the strategic. You're going to have to make strategic choices about which code you focus on, which code you try to upgrade and protect. And we need a solution which can be done in an incremental manner, which allows you to kind of pick and choose. So it's not an all or nothing solution. And so my sense of kind of how this approach works, kind of the recipe here, is basically you take C++, you define a kind of a safety dialect which is legacy compatible, and we'll break this down during the talk. You enforce for the first part in terms of strategically, new code has to be safe code. We've seen that new code is immensely responsible for new bugs, and so that's what you kind of lock down first, and that's also that you have much less kind of constraints. You don't have to go back. Someone's writing the code now, let them write it in this safe dialect. And then, to the extent possible, migrate your legacy code to satisfy, sorry, it's a typo, this safe dialect. And then you explicitly opt out what can't be migrated. So kind of taking inspiration from Rust's unsafe, you mark the code so that it can be audited, so that you can prioritize a list of trying to migrate that in the future and the like, that you have no kind of subtly implicit unsafe code. And then you profit or sleep easier. Okay, so that's all nice and good, but let's get into what we mean by safety, because I've been rather vague in that regard. So when it comes to C++, there's a long list of things we call safety, which roughly correspond to the long list of things we call undefined behavior. So I like to group together this first batch as memory safety. That's actually pretty common. I didn't come up with this grouping. And outside of that are still things we care about. So what am I going to focus on today are particularly within memory safety, spatial safety and temporal safety. So spatial safety is out of bounds access to an allocation. You have some sort of allocation. You want to make sure that any indexing into that allocation is in fact within the bounds of what you allocated. And temporal safety, which relates to things you've probably heard of, the idea of use after free or use after return. That'd be like a stack abuse, double free, and the like. And I'll get into kind of more refined definitions. And then outside of that, if you don't care about security or once you've solved that, there's still other issues to deal with. So one of the things we've been pushing on is also null pointer safety. This is responsible for a lot of reliability issues, and that's dereferencing a null pointer and ending up with a crash in your program. So I'll touch on that as well. I went into more detail last year, so I'm going to kind of just repeat that. I'll give a summary and kind of give some updates from that project. And just kind of give you the kind of the context for my work, at Google, we're dealing with a code base which is hundreds of millions of lines of C++ code. Within that, there are about tens of millions of pointer declarations, so spatial safety, temporal safety, null pointer safety, all deal with pointers. We have to look out for that. In terms of like migrating code, we have millions of files we have to touch. And then there's the human factor here, that we have tens of thousands of C++ developers. We can't just kind of, snap our fingers and say, oh, the world changes, do something different, move to a different language, or suddenly, everything changes from you. We have to work with them and bring them along. Okay, so let's start by talking about spatial safety and what we're doing here. This is, in some sense, one of the easier areas. What are the challenges of spatial safety? Again, roughly speaking, we have an allocation. You want to make sure indexing stays within bounds. We can break that down into kind of a few sub-areas. The key one being the kind of just indexing into any allocated container. But beyond that, if you want to be a little more conservative, you have to watch out for any pointer arithmetic. Because at pointer arithmetic, you calculate you start probably from some valid pointer, you do the calculation, you end up with a new one, and then later on in the program, you dereference it. At that point, it's kind of hard to know, is that safe? So if you want to allow pointer arithmetic, you're going to have to do some complex tracking of it. Or you have to make a choice, we're just not going to allow pointer arithmetic, just like we want to allow kind of raw container indexing. Then you have C-style strings. Technically, you could just say, well, they're not allowed because they're container indexing. But realistically, if your program, particularly legacy code, has C-style strings, you want to deal with those. And those don't tend to have size bounds information kind of moving along with them through the program because they are null terminated. So you want to have a different idiom to handle those. And finally, the bane of all memory safety, iterators. So iterators aren't just problematic in the spatial safety realm, because again, there might be some arbitrary pointer into a data structure. They also had touched on things like temporal safety because of invalidation. For spatial safety, we'll focus on the bounds aspect. But these are the key things I think you want to look at if you're talking about, what are the challenges of spatial safety. On top of that, there's the whole additional kind of orthogonal challenge of when dealing with third-party code, say open source code that you've imported into your ecosystem, because there, this whole notion of migration is harder or impossible, because you can't easily change third-party code. So you want to think about what can I do, can I accomplish without changing the code itself, say by changing the compiler. Okay, so how do we achieve spatial safety? The basic ideas follow that recipe from earlier. You define a compiler-enforced spatial safety mode. And notice this is it's not trying to solve everything. It's not trying to solve all safety. We can focus on spatial safety and say we are going to kind of make sure that C++ programs, when they have security vulnerabilities, spatial safety was not responsible. Okay, again, stick with new code is safe code. You enforce that with your compiler mode. You migrate your legacy code to satisfy the mode, and then you opt out what can't be migrated. So we've seen kind of in practice, you might have high-performance matrix manipulations. It'll be expensive to make those, pull out all the bounds checking. There you might use verification. You might use just validation. Someone looks it over. You use auditing. There's various approaches to, again, trying to be practical to areas in which you can't, or it's too expensive to make safe, but you have reasons to really believe you have high assurance regardless. Okay, so that's again, following the recipe. So what is this mode? To be a little more specific, there are two pillars. One is that it has to be modular. We, again, in order to accomplish our goal that be incremental, we want to make sure that you can look at one file, one translation unit at a time and ensure that it is spatially safe. So we go ahead and allow for the idea that you might call another function somewhere else which isn't spatially safe. So this code might not be spatially safe in its entirety, but we can kind of locally ensure that this code doesn't break any spatial safety guarantees, that all indices that are performed on the bounds checked containers and the like. And this is in contrast to temporal safety, which I'll talk about, which that's much harder. But here we actually can guarantee, at least in this code, nothing is violated, even if it calls somewhere else. And then if you want a binary to be spatially safe, you make sure you have another policy at the binary level to say all the components has to be spatially safe. Or I have reason to trust a few of them which aren't, or the like, but that becomes a binary level policy while we incrementally, kind of piece by piece, make the bricks, the components, spatially safe. And then again, it should be compiler-based. So that's actually not just enforcement, but the compiler can play an important role in terms of instrumentation. And we see actually both of those, almost like a balance of how much it kind of rules out and how much it brings back in by adding dynamic instrumentations that dynamically there are checks to make sure that you don't have any memory safety violations. As an aside, we find that you should design this to be AI compatible, but more importantly, it actually, I think, brings AI generated code into helps you along there, because it can ensure that anything it generates is safe, because you just reject the stuff that's not. If you just have kind of coding guidelines and norms and the like, again, the AI couldn't care less about your norms. No one's enforcing that, or you have to look for it in review. If you have a spatial safety mode, or again, any safety mode, the compiler can enforce it. That can all be done automatically.
Could I have a question?
Yeah, sure.
How do you ensure that AI-generated code is safe? I mean, I don't see any way to ensure that.
Right. So in general, you need some notion of definition of safety. You need that enforced by the compiler, and then it has to pass the compiler. If the compiler rejects the code because it's unsafe, then that's it. If it passes, then it's safe. The idea of the design of the compiler enforcement is that anything that passes is guaranteed to be safe.
But then it has no relation to AI.
Has no relation to that?
It has no relation to AI in that case, because the compiler is the gatekeeper.
Yes, the compiler is a gatekeeper, exactly.
Okay, so AI is completely out of the picture.
What I'm saying, right, which is why it's not like one of the bullets. The point is, it is, as an aside, a really important, I think, thing to develop in order to help ensure that the AI-generated code is safe. So human-generated code is already something we're dealing with. AI-generated code is even more of a problem because, again, it's just the amount, the quantity is off the charts. And so having an automated means by which to do that is extremely important just for gatekeeping. But beyond that, if you look at kind of agentic coding, they tend to use the failures in order to kind of go back and improve whatever code they're generating. So that actually can give you a feedback loop, which can help the AI get to safe code. But as a whole other discussion, I have some brief remarks at the end. Okay, so what is spatial safety mode? Basically, if you want something comprehensive, and again, the idea is that if the compiler passes the code, then we can be guaranteed it's spatially safe. You have to cover all of these areas. I won't read them all to you because in the next slides we're going to go into them. But these are the basic idea. And this parallels the kind of the challenges I mentioned earlier. Okay, array bounds checking. So for starters, we're proposing that the compiler bounds check C-style arrays. So that just like memory safe languages, the arrays are bounds checked. So the basic primitives everywhere are bounds checked. And that's specifically for statically sized arrays, those which the array is declared and the actual the size of the arrays is embedded in the declaration. That's great. Turns out it works. I'll get to that. The only problem is that there's something called flexible array members. These do not exist, right? They're actually not in any of the standards, and yet they're supported by most compilers. They're a holdover, carried over from C, and they're widely used in practice. And what these are final members of structs, which are arrays. If you're lucky, they're annotated, they're declared such they actually don't have any size specifications, just the brackets, and then you know it's a flexible array member. If you're unlucky, or you also zero, but if you're unlucky, they actually use an index, then you can't even tell whether it's flexible or not. But the key point is it's the last member, so when you allocate the whole struct, you allocate extra trailing bytes, and that becomes the space, the allocation for the array. And the problem with these is that it makes it hard, aside from enforcing the bounds for those, it makes it hard to enforce bounds for any trailing array member, which just happens to be in the last position. That it's not intentionally there, there's no specific semantics like flexible array members. But now when we see a final array member, we just have to guess, well, we could turn on enforcement and then maybe we'll be unlucky and start failing code which should pass because it's flexible. Or you just skip it and then all of those are unprotected. So part of our proposal for this spatial safety mode is to basically distinguish. You want to add syntax. So you distinguish explicitly. If it's a flexible array member, it has to be called out and defined as such. And then we can protect the other normal kind of statically sized members. And for the flexible array members, they should carry bounds information. Okay, so that's arrays. That's really only a small part of our problem. What about array decay pointers or dynamic allocations? So for that, we have what we call C++ safe buffers. The basic idea is use kind of the modern C++ idioms. You also rule out any pointer arithmetic or indexing. Again, we admit indexing is when it's really a problem. Arithmetic, we're being conservative, but this is a spatial safety mode. We're just going to rule those out. Find another way. And then you can go ahead and replace any use of pointer arithmetic or indexing with the various things like vector, or if it's a view, something like span. Make sure those are all size-bearing containers that you can turn on bounds checking for. We disallow any unsafe kind of containers or view constructors. So something like span, it seems like it's a safe thing once you've turned on bounds checking, but it turns out you can create a span with an arbitrary size. There's nothing promising that size is correct. And looking through our code base, which has a lot of these, I was actually surprised to see a non-trivial amount are really interesting creative calculations. So it's not like, okay, everyone just uses it in some really boring way. It turns out you really do want to be careful, and we feel that the mode should just say you can't use those. You always have to create a span or any similar view, like string view, from something else that was guaranteed to carry a correct size. This idea of C++ safe buffers was proposed by Apple back in 2022, and we started adopting it in 2024. Okay, then as I said, you need to use bounds checkable containers, but you also have to turn on the bounds checking. And so that's kind of a detail, but it's a difficult detail. You have to make sure you can actually afford the performance hit, but that is a critical part of a spatial safety mode. As an interesting aside, unique pointer to arrays does not actually carry a size. You can't bounds check these things. It doesn't carry that information. And so technically, that would just be ruled out by spatial safety mode. But we also have worked on kind of defining unique array, which is literally just a wrapper for unique pointer with a size, and also handles the allocation to be efficient. This is probably something we should get into the standard, or at least make generally available, so that users can continue to use this idiom even while being spatially safe. Okay, coming back to C-style strings. So in some sense, as I've defined it already, we're fine. They're just banned. Okay, so your code can still have a spatial safety mode. So that doesn't always work. You'd like to recover some of the flexibility. You want the compiler to understand the notion of a null terminated string and act accordingly, so it can say track the notions null terminated and look for the usage pattern around null termination rather than the usage pattern around bounds checking. So that's for some of them, and then migration is still a good choice here. Get to string view. I think many of us have been doing this already for years, continue that, but we'd like to allow both models. Finally, for iterators, again, similar to strings. Technically, like if they're a pointer, they're just going to be banned, so we're safe already, but in practice, you don't want to do that. For range for loops, you can already notice that pattern and allow it in any event, but going beyond that, you have to kind of figure out a solution, which there's a proposal available bounded iterators, which are probably the right choice in most situations, but otherwise Apple's f-bound safety, which I'll talk about a little more in a moment, could also be a solution for safely using iterators. Finally, most C++ programs don't exist in a vacuum. They integrate with at least some amount of basic C code. And so you want to make sure that your C code is safe too if you want to cover all your bases. You also need kind of something that covers the integration between the two. So we recommend Apple's f-bound safety does a great job for kind of a full spatial safety mode for C, but it's an open question as to, well, what do you do at the boundary? If you could integrate all of f-bound safety support into C++, but then you have this problem like, well, what are you actually recommending people use? Because the span now and f-bound safety support for basically annotating a pointer with a size, those are now 2 ways to do the same thing. Now, I realize C++ doesn't seem to have any hesitation with 2 or 3 or 10 ways to do the same thing, but ideally, if we're going to propose this, we would like to kind of give guidance as to when it should be used. So it could be that you do support the whole thing, but there's kind of style guidance. We're still working on exactly those details. Okay, so let's just kind of complete with a brief update on kind of migration itself and where this project, the spatial safety mode stands. So in terms of migration, we have 3 pushes going on. The largest one is spanification, and that is basically identifying raw pointers, which are pointers of buffers, and pairing them with their sizes, pretty much starting from arrays or similar allocations, and then tracing that through the call stack and updating all the points in the call stack to use span. We have a push to migrate owned pointers. So span is great if it's a view, but what if it's an actual, say, a dynamic allocation? So there you can actually imagine either it's already a unique pointer to array, and then we just need to clean that up as we discussed, or you can imagine just migrating it to unique pointer to array and then reduce it to a problem that's already been solved. And finally, we talked about those constructors we have to clean up. So there's some low-hanging fruit. You see a common pattern that I've shown here, where you have a span where it actually takes a container and gets .data and .size. That's easy. Just use the single argument constructor. There are a lot of these. Beyond that, spanification will clean up a lot, because you have a situation which is taking a pointer. That pointer will be identified somewhere upstream in the call stack as coming from some allocation that we've already been working on spanifying. The span will reach that point and replace it. And the rest, that's still an open problem to solve. So where are we? The spatial safety mode I've outlined here, we have written down in an RFC. We're going to publish that to the Clang community, starting with the memory safety working group, kind of get their feedback, and then going to the broader group. I hope that can make its way, assuming it's successful, into the broader C++ community. In terms of implementation, Clang's unsafe buffer usage, so it's a warning, not a F-W, unsafe buffer usage, captures most of what we talked about. We've been extending that. Kudos to Apple for most implementation work there, but basically that's just a lot of it. We need to kind of finish that off. In terms of hardening, at Google we've enabled bounds checking for the C++ standard library. More recently, we enabled bounds checking for proto-buffers, which are a major part of our workload. And we've seen minimal performance impact. The overhead is about 0.3% on average, came actually lower than we'd anticipated. This is perhaps more interesting. We enabled primitive array hardening across the fleet, and we saw something like 10 issues, like 10 things we had to work out. So I guess in general, statically sized arrays are used well, or we just got lucky. Either way, this was a really interesting and encouraging result. In terms of migration for the owned pointers, we're near completion of migrating owned pointers, a unique array, a unique pointer to array to this unique array. And recently, in the past few months, we've started landing PRs in our codebase to spanify our pointers. We already have a few thousand, and we have that's a few percent where we're making our way across the codebase. Okay, let me pause there. Any questions on spatial safety mode?
So is it like basically enabling bounds checking for arrays, like for vector add, just for all arrays and pointers, and you also like add span to ensure that you can actually do it for row pointers?
Yes, although I think there should also be some amount of instrumentation from the compiler for things like local use of pointers where you know the bounds. So this is kind of the boundary with C, and that's inspired by f-bound safety. I think for iterators the same. You can there are places where you actually do know the size. The compiler can know the size, and instead of banning that and then making someone rewrite the code, I think there's instrumentation which can widen the pointer and then track it, dynamically track the length, essentially creating a span implicitly. So that's promising both. In terms of less burden on the developer, but also in terms of third-party code, which I didn't get into. But all those compiler instrumentation solutions, they apply without cost without static cost to third-party code.
Do you have any estimates on like how much code is affected by this compiler instrumentation? Like, is it, I don't know, like 1 line in 100 or 1 line in 10,000 lines?
I know how many unsafe buffer warnings we have. I don't know that I can share that information.
Like popular, not popular, popular in particular areas?
Yeah, I mean, if you're writing in modern C++, thankfully, for the most part, you don't use this. So it actually is not a terrible problem. It's enough that we want to stamp it out, particularly since spatial safety is overrepresented in terms of vulnerabilities, possibly because of being low-hanging fruit, but it's a real threat. But yeah, in general, if you're using modern C++, you're in a pretty good place.
So it's mostly for codes that hasn't been spanned yet.
Yes. Yeah, exactly.
Is there a way to optimize this, or you like do manual effort for migration?
Right. So we don't have. I mean, the code base size is again hundreds of millions of lines of code. So we don't even. It's not even optimized. We don't have the choice to do this by hand. So this is all, right now it's Clang kind of AST-based analysis. It's a 2-part analysis. I didn't get into this here because we had a talk in October, the LVM meeting. So Wante gave a talk in detail about spanification. I talked about it last year as well, so I don't want to repeat that. It's I think, really technically interesting about how you do that and whatnot. I'm happy to talk to you afterwards, but I didn't get into it here.
So I know that Google uses Abseil a lot, and the Abseil span has additional capabilities that aren't in STD span. Do you guys, for this part of it, take advantage of any of that? Because I think there's like some safe constructors or something, if I recall looking at it.
I should know the answer to that. I don't remember anything special in that regard. Mostly it's just that it supports null putter, or vice versa. The major difference has to do with allowing those constructions.
Okay.
So yeah, we do plan to harden Abseil span as well, but beyond that, we're not taking advantage of any particular feature.
Oh, so you're actually, the stuff you're talking about here is actually STD span.
Yeah.
Okay.
Okay. Cool. Okay, let's move on to temporal safety. Okay, so why does this matter? Again, as I said, low-hanging fruit, or kind of the major thing we see in terms of vulnerabilities is spatial safety, but temporal safety is still an issue. This was an analysis of 912 basically key bugs in Chromium since 2015, and we found that about 36% of them are use after free, which is kind of the main temporal safety violation. So this is pretty significant and something we want to close that up. So can we just follow the same recipe? We define some temporal safety mode, make sure new code is safe, migrate, opt out, etc. Sounds good. I'd love for that to be available, but it's not so simple. If it was that simple, we would have solved it already. Again, if you've been in the community and heard of these conversations, this is a much harder problem. And the key point is that this incremental property, which we have a spatial safety mode, where you can say that at least the code in this function is fully spatially safe, even if it calls out to some other function which is not, is much harder to say for temporal safety because it's all about, again, temporal, about time, about how the pieces of your code interact. So we'd like to get there. We are working on that as an aspiration. But for now, we fall back to what we call lifetime safety analysis. And that is already built into Clang, and it's very effective. So this is not a full spatial safety mode, not full temporal safety mode, but it is already quite effective in finding and preventing statically a significant range of common mistakes. And we think we can build on this to get to some practical temporal safety mode. Okay, we should go back. So what I'll do for the rest of this section is basically two things. One, get into what is temporal safety, kind of build intuitions behind it, and then also use that to inform and tell you about the Clang, this lifetime safety analysis, which captures some of those ideas. Okay, what's the definition? I think the easiest one to say is that it's undefined behavior to access memory after it's been deallocated or freed, whatever you call that. Perhaps that's not quite true, right? Because let's say imagine you just had one piece of memory, and you allocate it, and you free it, and you allocate more memory, and then you use that same memory through the new allocation. That is totally fine. So talking about the memory is not actually the right language for what you're describing. So what I'd like to do is go through the intuitions that developers have around temporal safety, and we can come back to a more refined model and see how that turns into an analysis which can help us solve these problems. Okay, let's start with an example. Some basic code. We start with a pointer up top, and then there's a new scope, and that's important, with a unique pointer in it. We grab an alias and the like. So here's unique pointer. That's a new allocation, but it's in that scope, so we know it's going to be destroyed at the end of the scope. Here we grab an alias in P. At this point, it's destroyed, right? Now we've used it. Okay, so let's see the programmer's intuition, about that program. First of all, you focus on when the object is destructed. And then you work back and you say, well, if it's destructed there, I have an alias above. But that's not necessarily bad, because an alias can be dead. It doesn't mean you use it. So now you go looking elsewhere in your program. You say, no, nope, it is used later. Since it's used later, that's a problem. Okay, so those are the key ingredients of kind of reasoning about temporal safety at the local kind of function level. And we'll map those to the following three higher level concepts: invalidating operations, the notion of aliasing and points to, and finally liveness. And let's look at each of those in turn. Okay, so invalidating operations. So first, running a destructor, right? So here we have a scope. When the scope ends, the destructor is automatically called. The compiler inserts that call. And now, like in the case of make unique, that means the object is freed. In fact, for most objects, when the destructor is called, any memory is freed. So that's very nice. That's very clear. But you also have destruction, which happens beneath abstractions. So this is a classic one, where you have pushback on a vector, and that reallocates the underlying memory. Copies over all the elements, and any outstanding references you had into the vector are now invalidated. Can I just get a show of hands for who hasn't been bitten by this bug? Impressive. Okay, yeah, because I definitely have, and not just once. So it's a very common mistake. At this point, I can recognize, when that kind of thing has happened. And therefore, a pretty critical thing you have to account for in any sort of analysis. Okay, let's talk about aliasing on points here. So here, that line, again, where we alias the allocation of x with p. We can imagine there are more aliases. That was just one, but we go through some arbitrary chain where first you put it in q, and q flows to p. This is a very simplistic example. This could be a 300-line function. It could cross function boundaries. So aliasing in general can get very rich and therefore make reasoning a little tricky. We can also invert that. So that's the idea that you have one object, multiple aliases to that object. You could also imagine a single pointer has multiple objects to which it might point. So here we have p again. We start by referencing a new parameter. We just grab the address of parameter I, and now we conditionally run the code we just showed. And therefore, by the end of the code, p might point to either x or I. Okay, and finally, liveness. So here we've changed the code. We've added another unique pointer allocation, and now we alias that new one y. Okay, so that new alias to y actually overwrites the previous alias. So it kills the previous value. So p equals x.get is no longer alive, and it doesn't matter when we get to the bottom, when we dereference p, that's actually fine. So this idea of liveness is critical to the intuition and to any sort of analysis. Okay, so we put it all together, we can get the following lifetime model. The first one, and this is I think the critical difference from that kind of idea I presented for the first definition, is that we don't talk about memory. We talk about abstract objects. So here on the right, I've kind of mapped out what I've been saying informally a little more explicitly. If we have an int x, we can say the story for x is an abstract object O1, so that if you take an address, you're pointing to that object O1. And Y would have a separate one, O2. Z is going to point to an allocation. That's another abstract object. Well, basically, you can map abstract objects to any particular point in the code. Some analyses might be actually more precise. They might actually say, look at a loop, and then you only have one abstract object. And they might say, well, I want to distinguish. They might distinguish some number of dynamic instances. However you do it, the idea is that you think in terms of abstract objects and pointing to abstract objects. And that brings us to points to sets. Points to sets, say for every pointer, actually every pointer expression, you can think of what are the potential objects that this points to. Invalidation, that's a key part of the model, and that tracks essentially the lifetimes of abstract objects. Finally, liveness talks about the GL values that actually store points to sets. If it's just an R value, we don't really care because it disappears as soon as it's used. But GL value, you might grab essentially a pointer, an alias at one point in the program that could be invalidated later, and then if it's used again, that matters. So we have to know, is the GL value still live at the point in which the alias is created. And finally, I'll note that this is all flow sensitive. There isn't one property for the whole program for a given variable. We're looking at every program point. We're asking questions about what's valid and what's not, what points to sets are and what aren't. Okay, so summing this up, we can put together a lifetime policy, kind of our definition of, here again, temporal safety, saying that you violate the lifetime at a given program point P if, first of all, you have an object which is invalidated at that point. You have a points to set S, like any live points to set which contains O, and again, that S is live at the program point. And that gives you the kind of colloquial way of saying this of a live points to set should not contain an expired object. That's one way of framing it. You kind of try and express it intuitively. You could look at it from the perspective of use. There are many ways you could do it. I think this is a nice way to kind of capture it succinctly. Okay, so let's kind of step through how does that work, looking back at our program or a slightly simplified version. First, I just want to point out that I've named the points to set for P just so I can call it succinctly S. S starts as the empty set because it doesn't point to anything. Okay, so first of all, again, invalidation. We see that the object O is invalidated. At that point already, S contains O. You can see that happened at the alias. So when you grab the alias, say, well, I've updated the points to set S to be exactly O. And if it's conditional, then it would have multiple things. And then finally, we get to this idea that variable P is live. Again, just reviewing what we saw earlier, but with this new language. Okay, so now let's jump to actually a demo of how this would work in Clang, and that's why I kind of sketched that out. Basic idea here is that when you have a problem where you use something, say, from the stack, which has been destroyed, it will actually highlight each of those steps. So it'll say, oh, you just grabbed a view, which is, say, an alias too small. That object doesn't live long enough because it's going to be destroyed right here. And then it'll furthermore tell you where it's used. So again, this is a very trivial example, but can handle significantly more complex examples that will look at all, basically the entire function scope and reason about that. If you want to try it out, there's links at the bottom. I think these slides will eventually go live, so if you have to look it up. If you want it sooner, by all means, come talk to me.
How new is this?
Sorry?
How new is this?
So I'll get into the lifetime annotations in Clang, which are a few years old. This lifetime analysis is a few months old.
Huh.
So pretty rapidly developing. We're constantly adding new features.
I just have this funny feeling like it's been there for a long time.
The annotations have. But still, it's like 2 or 3 years. So the annotation only supported at the expression level, and this expands it to the whole function scope. So this is a totally new implementation. Yeah.
How large is the compilation time impact of these analyses?
Yeah, that's a very good question. I don't remember what the most recent thing was. It's a few single-digit percentage. I can't remember if it was on average or at most. It might have been 4% worst case we were hitting.
Okay.
It was well within the bounds of Clang's tolerance. It's not turned on by default. You have to choose to turn it on, but it was surprisingly low. Okay, so this is all great for local code, but we don't write local code. Everyone calls functions, right? So what can a function call do that's relevant here? Well, 2 things. First of all, it can add aliases. In particular, it can return, say, a pointer which has a whole rich alias set. And now you don't see into that function, you don't know what that alias set is, that points to set. And it can perform validations, pushback, right? I mean, that is a classic problem. Okay, so for this, you really want a system to capture those somehow with essentially some sort of lifetime or temporal safety contract. You want a compositional analysis, so you don't have to look into the code. You can imagine you just unfold all the code. Actually, the current analysis would support that. It would not scale. That would be some sort of interprocedural analysis. And even interprocedural analysis with summaries, still, I mean, ideally, you would annotate in the code itself some of the actual contract, because that gives information not just to the compiler, but also to your developers. So basically, you want to extend the language somehow with some set of annotations which allow for these kind of API contracts that can capture these two key points to sets and invalidation. What I've been calling points to sets, in terms of mapping back to, kind of, say, Rust language, it would be a kind of a lifetime. A lifetime, in essence, maps either roughly or exactly onto this notion of a points to set. Okay, so that's the basic idea of how you would handle functions, but that leaves a lot on the table. So I think that what I've presented so far aligns with what we have in the analysis, but it really is just the beginning. Okay, so we have a lifetime policy. You can see how that kind of analysis could enforce it. I've talked briefly about how it can extend to functions, and that's great. And we can find a lot with this analysis, and we can stop a lot of badness. But what is fundamentally missing is that if you have a rich data structure, it can have many fields of its own. It can have fields which point to other objects, which have in turn many fields of their own. You can end up with many, many references, and you would have to track a lot of different potential objects and their points to sets. You need some form of abstraction to deal with this. And this is where you see something like Rust's exclusivity rule come in. It kind of collapses the complexity by essentially forbidding certain behaviors which allow you to then just categorically not worry about certain kinds of misbehavior. So we don't have that yet. That's something we still need to work out. But I have hopes, since there's so much effort in this space, that there is some mix of something like exclusivity with the incrementality that we're looking for that could get us beyond just what we have today.
Would you mind giving an example of where Rust exclusivity rule helps, but like in C++ code?
Yeah, so let's say no. I mean, if you have a lot of references and you try to track the invalidation of each one, if you start thinking about how that works when the references are, say, in private fields or nested deeply, the amount of information you'd have to track becomes unwieldy. And so the exclusivity rule helps in the sense that it doesn't allow you to ever grab a writable reference. Like the reference can't escape into some object. It can't end up being nested deeply in an object because you can't have you couldn't have, say, a read reference escape into an object and then worry about invalidation happening, because you can't have an validation means you have a mutable reference. That by exclusivity, that read reference can never appear in the other object. So it just rules out the idea that you could have a rich object with all kinds of reference of basically pointers to other objects which might be changed, and therefore you have to track their invalidation. So really that's not quite an example, but that's the intuition. I think on code it would be much easier to see concretely.
So basically we don't care about read-only references because they can't invalidate the object, but we care about write references that can invalidate the object.
Yes.
And that's where it helps.
Yeah,
okay.
And I will say, like, Alon's talk tomorrow, is it? Yeah. Is going to really get into this, and I'd recommend going to that to get a proper kind of discussion of exclusivity and borrow checking and the like.
Thank you.
Sure. Okay, so let's talk about the claim lifetime contracts. And the basic idea here, and this kind of gets back to your question about where do these exist, we'll see them in a moment. One thing they can express is aliasing. So here are two very simple functions. One is essentially the identity function. It takes a reference to a string in and returns it as a string view. The second one is a little more interesting. It takes two references in. The only one it can actually return a reference to is in. Okay, so it strips the suffix. The suffix is information that's read-only. It will use that to potentially strip the suffix off of the incoming string.
I have a dumb question.
Yeah.
Why are the parameters not string views?
Just to demonstrate. Yeah, they could have been as well.
Sorry for the interruption.
No, that's fine. That's fine. Good. Okay, so you could imagine, say, like a type-based analysis in which you just say, well, if they share the same type, we're just going to assume any strings that come in could go out. But with annotations, you can be a little more specific. So again, these are not Rust-style annotations. They're very limited in what they can express. But it basically says this parameter is bound. Its lifetime is bound the lifetime of the return value. Or more of the point is the return value is constrained to share its lifetime. And so that allows you to express both the identity function, but also the more refined point about strip suffix being different. And again, the key advance we've had here, kind of the recent work on the lifetimes analysis, is to allow us to enforce this at more than just a expression level. Okay, let's talk about invalidations. So, as I said, pushback, clear, insert, those are just vector operations. They can have this, this impact on temporal safety. Okay, so for starters, we hard-coded support for a variety of kind of STL libraries. Vector and unique pointer being, I think, the key places we started. But we really want to kind of go beyond that and actually allow you to express these as contracts. Like something like the syntax would be something like Clang invalidates, and you would reference back to what's affected by the invalidation. That's something we're still working on in terms of the particular syntax, but that also would be the kind of the second part. So the lifetime bound tells you about aliasing. This tells you about invalidation. Overall, let me just kind of summarize what the analysis does. And basically, for starters, it's based on Rust's Polonius algorithm. So I stripped out all the Polonius kind of nomenclature, which has to do with borrowing and loans and origins. And that is important for exclusivity and borrow checking, but since we're not talking about that, I kind of just pulled it back to kind of more traditional aliasing and points to sets. But the actual implementation is, uses that language and is based on the Polonius algorithm. In terms of what it supports, we have kind of full support for smart pointers, understanding their semantics, fields, so you can actually have paths and not just variables, globals, lambdas, stood function, and we are constantly adding more C++ features. The diagnoses, again, we don't do full temporal safety. What we have is return, we diagnose and return a stack address, so any of those kind of scoping, local scoping issues, which is a significant issue. In general, use after scope, use after free, those, when we see it locally, we can diagnose those. And then a little more conservatively, we talk about liveness, and that's great when you actually have visibility in the local function. But what happens if you assign something into a field and then you don't see what happens, or into a global? So in that case, we'll actually we can report an error on those as well. It could be outside the function, they're never used, but because they might be, we want to be a little more careful, so diagnose that. And then finally, again, we do track STL container iterator invalidation. Excuse me. Okay, and finally, because no one likes writing contracts, we have two features that just fall out naturally from the analysis. It's precise enough that it can actually figure out and infer contracts for you. So you can do this in two ways. One is just to do it implicitly, like within a TU, look at all the internal linkage functions, and kind of as it goes through those in such a call graph order, infer the annotations, infer the contracts, and then enforce those contracts in anything that follows. And that can be very powerful in increasing, essentially giving you an interprocedural analysis. But for, say, functions which are not internal linkage or exposed to other callers, you might actually want to add those contracts yourself. And so for that, we can give you suggestions. We've inferred it. We'll give you kind of edit suggestions for where you can put your contracts. In terms of what's coming, again, user-defined invalidation I mentioned. You also, once you put a contract, it's all well and good, but code moves on. So we want to actually verify the contract matches the implementation, which we can do. Again, we have this full visibility. We want to support async functions, nested lifetimes, kind of lifetimes, and we can point to an object and then have a lifetime in that object, and higher field sensitivity. And I'll close by saying, again, can we get to a full temporal safety mode? We'd like to. This I think is kind of what we ultimately are aiming for. This is something we kind of said in one of our annual goals. We'll see. That is something we're very excited about, but it is still an open question. Okay, you can find out more on the Clang website. All this work has been done upstream from the beginning, the original RFC. You can follow us on Discord and participate if you're interested in contributing. We'd love contributors. We have multiple non-Google contributors, whether reviewing or actually submitting patches. Okay, that's it for temporal safety. Any additional questions? Yep.
What sort of time frame was all this code written that you're upgrading? Is it like all pre-2000, all pre-2015?
I mean, we're constantly generating code. The graph of new C++ code is kind of scary in its shape.
Yeah.
It used to
but-
track the developers, number of developers. So I don't know how much pre-2000 code we have left. Probably some. I would say probably mid-aughts and on. There's definitely stuff that survived from 06, 07. We still have things like that. Some of the core abstractions might live on. I mean, they keep getting upgraded, but that code still lives on. So it's everything from probably early to mid-aughts, on.
So you're still having lots of new code written that these new checks is catching.
So we've only recently written these and rolled those out. So the new code, we're not enforcing them on all new code. So no, we're aiming to kind of make this globally on, but it's not yet.
How much code is opted out of this forced lifetime checks? Like I can imagine if you have, let's say, a thread pool and you submit tasks to it, then lifetime of tasks, captured variables, and thread pool itself becomes very tightly coupled. Is that an issue that you have to opt out, or is it covered?
So this analysis is actually quite conservative. I would say there's very little code I can imagine opting out. I would imagine that more once you try to get to a full-blown analysis, which will literally just reject, kind of define some temporal safety mode. That's where I would imagine if some things which don't match, like the example you gave, then it doesn't fit the pattern. We'll try to fit as many patterns as will work in this model, and otherwise you might have to opt things out. But currently, yeah, this is quite conservative. It's finding real bugs.
Is replacement of the compiler, could it help, like Carbon or whatever the language, like with backward compatible rules, could it help better than those rules?
So can you expand on that?
Yeah, so I don't know, so you mentioned Circle. So Circle is kind of backward compatible unless you start and write new code, right? So is there a way to just use this compiler and maybe have a more benefit, like a complete Rust way of defining out the errors, the vulnerabilities?
So do you mean the current, could you use the current analysis in all new code? Or do you mean something that goes beyond that?
I mean, something that goes beyond, like the threat safety and the rules that, let's say, Rust enforces.
Yeah, so that's our hope. That's what we're aiming for. This just takes time to develop, and again, it's an open question whether you can actually, define one that's going to work well with, for new code and for existing code. So I think it will look something like, Circle's model. It just has to be more permissive. So, for example, I could imagine we're working on basically dynamic analysis for temporal safety. I can imagine you put the two together. When you can statically ensure the safety of a pointer, you do that. And when you have, say, some legacy code you're calling and it has an unclear, alias set that's returning, you would then you make sure that is dynamically, tracked. So something of that sort. That's where, again, I don't want to criticize Circle. Actually, I'm a big fan of it, but I think it breaks down when you try and integrate it, really integrate it into your existing code.
So one of the things you said at the beginning was like, I want to move to a place where the new code I'm writing, I can be sure has some safety characteristics, and maybe the old code is old, so I just have the time-based, like I would have found the bugs by now.
Great.
So like with this kind of analysis, it's okay. I can add these annotations and I get these checks, and that's great. But like how do I know that the new code is good?
Right, you don't. This doesn't give you. This tells you a certain class of bugs it has ruled out, like return stack address, the ones we've listed. It knows that are good. It's probably reduced the likelihood of other mistakes. But yeah, if you have a pointer that's coming from another function, you have no idea kind of again what the point Sue said is, or if you misuse the protocol, it's not going to capture that. So I think there's one level in which we extend it, like with vector, where we've annotated pushback. I think some level you can kind of keep adding to the current analysis so it can see like a shallow temporal safety protocol issues. But I think if you really want to ensure the new code is safe, you have to solve the problem.
Does it make sense to use this thing together with address sanitizer, or it is a superset of address sanitizer?
So address sanitizer has like a 2 to 4x overhead, including RAM. Now there's a massive RAM crunch now, because probably we know that, but not like that's a major problem. Even for a company like Google, we can't just kind of throw RAM at it. Even hardware ASAN, which is only available for ARM, but let's say you're working on ARM chips, that brings it down to like 2x overhead. So it's very powerful, and we use that in various places, but it's not really a solution across the board. It could be you're running in a setup in which 2 to 4x overhead is fine, right? And in that case, yes, I think that's a good solution.
Yeah, I mean, like, if my code compiles with this lifetime safety checks passed, is it probable that address sanitizer will find any new issues, or there is a guarantee that there are no lifetime issues?
I'd say it's possible. There definitely is not a guarantee. But I mean, the key problem we've thought of is you can't just it doesn't have a gradual way of working together. It's not like you can say, well, here I don't know, I haven't statically enforced it, so let me use ASAN. ASAN is all or nothing. So that's the thing. We are developing a new technique, kind of a lock and key technique, which for other reasons we're developing it. But I'm thinking, maybe that would actually work out, where you can kind of choose which pointers you protect based on what you see from the static analysis, where it's not confident that it's enforced the safety. Okay, so therein ends the memory safety portion of the talk. If that's what you're here for, you're welcome to go. From now on, I just want to talk briefly about null pointer safety, and this is really about reliability. So there was a great talk last year in which someone pointed out that because of undefined behavior, if you have a null pointer safety issue, you can actually do anything. I think launch missiles was the example the speaker gave. This is true, but no one really believes it. As in, we have not seen this in practice. And if you're trying to motivate null pointer safety work because of memory safety, you won't get very far. And I can tell you that based on experience. So it's a real concern, but this is a reliability concern. These are the crashes that all kinds of services at Google see and care about, but is distinct, I think, from memory safety. Okay, and the basic problem here, I'll run through this quickly, is that C++ conflates this idea of you require a value from, it's optional. And it's not just that it does this by default, but there is no way to distinguish. It's not built into the language to specify, one way or another, what the semantic, what the contract of the pointer is. And compare that with, our familiar int versus stood optional int. Stood optional arguably is built into the library, but still, same idea, that you have the ability to express these two separate concepts. And we have double-digit percentage of our crashes in C++ binaries are actually due to just simple null pointer dereferences. So very much something we would like to fix. The basic idea here is we use annotations. So Clang actually added these a few years back, which call out essentially the three semantic states or possibilities for a pointer. One is that it's non-null, which says that null is just not a valid value for this pointer. The second is that it's nullable. Null is totally valid. And this aligns with your intuition about kind of the standard. If you see a raw pointer, you think it's valid. But the key point is the way people use pointers goes beyond that. And that kind of the contracts of pointers are not just any pointer can be null. We have an intuitive notion that some are non-null and some where it's actually valid, just again like int and optional int. But again, we have all our legacy code. For the legacy code, we need a third state. We need to distinguish the idea that actually this pointer, we don't know what the contract is. We don't know which one. So then again, it might be null, but more to the point is we really don't know what to make of it. That ability to kind of call out legacy code is really important with this idea of kind of incremental change. You can move through your code base and improve things while still understanding what you've changed and what you haven't. As it is, for our analysis, we actually treat anything legacy, unspecified, optimistically. We don't assume it could be null. We basically, assume anywhere we use it, it's essentially unchecked, not quite. You basically turn off checks around legacy pointers. Okay, so let's just see how this looks in practice very briefly. In the first line, we have foo, and we've marked that p is non-null. It means no caller is allowed to pass something which might be null. A bar, in contrast, says it's totally legit, and if you're a caller, you have to check for a null return. And then zab is just unknown. It's a legacy pointer, and we leave that implicit. Okay, so we have an analysis written in Clang tidy, actually. Very trivial examples. The first one is that you've marked a pointer non-null. You dereference it immediately, and we don't warn on it. And this might be obvious, but the idea is we're not being conservative. We're saying if you've marked it non-null, we're going to trust you and not force you to check it. There is like the defensive coding, which is always check it, and we're saying no. So it gives you that flexibility. If it is marked nullable, then clearly that would be an error. And then how would you fix that? Well, you have to check it. And on the right, you can see the example where you've checked that P is not null, and only then do you use it. At that point, the analysis essentially puts it in the non-null bucket, and therefore allows it just like any other non-null variable. Yes?
So maybe I'm jumping the gun here. So if once I check P for null pointer and it's not null, does it basically become a non-null pointer? So can I call a non-null function with that argument once I check that?
Yeah, you're not jumping the gun. Yeah, yes, exactly. And it's not just there. So let's say you said if P equals null return, then anything in the rest of the function, be it 100 lines, be it 1,000 lines, as long as you haven't overwritten P, then it will still honor that. It basically changes its fundamental representation. It says, I know it's not null, and then you can use it throughout. And this is really important for C++ code, right? I mean, if you look at other kind of memory safe languages, newer languages which have a distinction between null and not null, it tends to be you only allow that kind of in a local scope. Once you've checked it, and then you can use it. But C++ code doesn't really follow those rules, and it's very common you'll check it once in the program, in the function, and then use it throughout. So we make sure to support that. Okay, so that's nice. This analysis is great if you have the annotations, and if again it's nullable or non-null. But if you have these unspecified, these raw pointers, kind of the traditional legacy pointers, and you're writing new code, then anytime you write a pointer, that is again implicitly unspecified. So ideally, we would be able to kind of lock in null safety by choosing some other default for a raw pointer. So we looked at our code base. Some of this we did by hand, like sampled a few hundred pointers, and then through an analysis, which I'll talk about in a moment, we actually looked at our entire code base and looked at all the third-party code we import. And we found there was actually like a 6-to-1 ratio of non-null to nullable pointers in our code and 4-to-1 in third-party code. So a pretty significant imbalance. So for that reason, we actually have chosen that non-null will be kind of the default meaning of raw pointers. Not now, like the code is still as it is, but we are aiming to kind of get to that point. And we support changing the file default for that reason. Yes?
A question about this. So my understanding is Google's approach to passing mutable parameters is by pointer, right? You pass it by like a mutable pointer?
Not anymore.
Not anymore. Okay.
It was, yes, and eventually enough people rebelled and we reconsidered our life choices, and yeah, now we mutable references are okay. So yeah, so actually it is important to note, so we say this like a lot of those should be moved over to mutable references. It still comes out, even if you account, you do a three-way analysis of basically non-null should be a mutable reference, should be nullable, you still end up with, I think it was roughly 2-to-1, nullable pointers to non-null. Is that where your question was going?
Yeah.
Okay, yeah, absolutely. So yeah, I mean, ideally, in fact, a lot of the stuff we detect, we would then have a follow-on project which trivially kind of converts those to references and just updates all the callers. And that is, I think, for kind of code health perspective, a good thing to do. If we had more people on the team, we definitely would be doing that. Okay, so we kind of chose that as our goal, that you can do non-null, and we support it. There's a pragma you can put in the file, and then the analysis will interpret it as non-null. We haven't gone there yet. That's kind of the end game, for this project. But we think that is really critical to kind of, and then that gives you a null pointer safety mode. Okay, so that's great if you have all these annotations. We said we have a legacy code which doesn't have it, so we'd like to infer the contracts on the pointer types from the code base, but again, given only the source code. Comments tend not to be terribly useful, more like there aren't that many comments which really specify the null pointer kind of null contract. And we also want to avoid kind of a human in the loop. When we have millions of lines of code, we don't want people having to review and make the decisions. The basic idea I'll go through quickly is just that you look at uses in your code and you extract what we call evidence, from particular things that are null relevant. I have some examples here on the bottom. You can imagine foo, and it takes a parameter p, and then you use p without checking that it's non-null. So we're going to infer, it could be a mistake, but we're going to infer, and it's usually right, that the intent is that p is a non-null pointer. And then for nullable, well, if you see bar called with some pointer, either null itself or something that could be nullable from the analysis, then you're going to infer that bar's parameter p is nullable. Okay, so that's the basic idea. There are many more classes of evidence, but that's how we add it up. And then you see these local information, then you propagate that through the code base. So you kind of keep iterating through the code base. Find in practice about 6, 7 iterations will get you to essentially a fixed point. Okay, so let me just kind of quickly say where we are. And again, reminding you that we have tens of millions of pointers and millions of files. So the analysis itself, we deployed this in 2024 on all code review. And we still do not have a revolt from users. People are pretty happy. It's about, I think, 1% rate of people clicking not useful. We don't have that many. We have like a small collection of false positive bugs, which we kind of slowly burn down, but it hasn't exploded or anything like that. It seems quite stable at this point. We also see, like rather excitedly, we're seeing that some projects have organically started adopting default non-null and seem to be quite happy with it. And that's an order of maybe 1,000 files or something like that. So it's new, but we're actually seeing that movement. We, again, hope to get the whole code base there, or 90% of the code base, but that is a good early sign. And really interesting this year, one major project, about 30 million lines of code, was actually able to trace using the system to actual reduction in crashes by about 35%. They added 2 key features. One, they went ahead and actually fixed all the violations our analysis finds. And then they also made code review, that code review check we've implemented, they made it blocking. So you can't submit if you've introduced a new null pointer problem unless you override it. I mean, the system always allows for overrides, but by default, you would have to explicitly override the check, the pre-submit check.
Are these crashes replaced by something, or it's with your election? For example, if you check for null and then, let's say, you abort gracefully or terminate the application, then it's not a crash anymore, but it's still a failure. So is it like genuine bug reductions, or it's just a replacement?
Genuine bug reductions.
Okay.
I mean, yeah. So it's not. I mean, generally speaking, when you, I mean, check fail is also, the assertion failure is also in the same bucket. Yeah. Okay, for inference, the major, I'd say, progress since I talked about this last year is actually productionizing it. So it went from something that one of the team members would just run occasionally and keep running to collect data, to something that we run regularly and actually now using to roll out over the code. We've covered more than 20% of the code base. Specifically, we targeted the nullable annotation. We're adding that first, and then we're going to come back and add the kind of the default non-null. That'll be kind of a phase 2. One of the interesting things that came out of this is that, again, we're iterating 6 or 7 times over the code base. It's really expensive to parse C++ and leads to all kinds of negative knock-on effects. So we actually rewrote the core analysis to basically have a pre-phase which looks over the code, extracts all nullability relevant information, puts those in what we call summaries. It's kind of a standard approach in static analysis. And then everything else, all iteration, is driven off the summaries. The inference itself now scales to nearly all of our monorepo. That's not one process, that's thousands and thousands of processes. We can infer contracts for more than 80% of pointers. There are multiple reasons why we can't get to the rest. Probably the largest group is just that there's code which even as a human, if you look at, it's not obvious what the intent is. And there's nothing forcing it one way or another. So like you could choose something, might lock it in for the future in a way that the developer didn't want, but like the information literally just is not there. We're seeing about 2% rate of conflicts, and going back to the earlier trivial example, imagine if foo, uses p such that it must be non-null, but then it's used elsewhere, it's called with a nullable pointer. Well, who's wrong? Is it a bug in the implementation of foo? Is it a bug in the caller? So that's a conflict. There are many reasons conflicts can arise, bugs being one of them, but also usage patterns that we just don't support, or places where our model is just not precise enough. So actually over the course of this year, we were able to reduce, and I'll talk about that in a moment, the conflicts. Let's get to that. Okay, so just quickly some practical insights from having run this now for a year. And this is the most, I think, interesting one. We started, we assumed you want to have... Yeah.
Before you go ahead,
sure.
One quick question. Obviously, this is all about raw pointers, and you have the same practical problem with smart pointers.
Yes.
And has anything been done in that realm?
Yeah, so I should have said it earlier. Yeah, we support unique pointer, and in fact, anything with the nullable annotation, as far as I recall, is supported. Although, I suppose in claimed you can take nullable and apply it to a class definition. And then it gains kind of the nullability properties. You can apply non-null and nullable on APIs, anywhere you have a declaration. So we explicitly support raw pointers and smart pointers. Some other things I think as well. We don't support the full range of anything a user is going to put on, because you want to, I mean, you can in some sense, but if it doesn't look like a smart pointer, then it's a little more complicated. You'd have to know the semantics of each thing, of each class.
So, but at least unique and shared.
Yes, I think anything is smart pointer, fairly certain, as long as it has essentially the smart pointer, duck typing.
Yeah.
We'll support it.
Gotcha.
Yeah. And we have done more. In fact, that project, which reached the 35% reduction, one of the things they did is their engineers actually added some of their special smart pointers. They added support into the analysis, so it was obvious as well. Okay, so I think one of the most interesting things we saw was that when we started, we said, tests are kind of the gold standard for what is the range of behaviors of a piece of code. And that sounds, nice, but it turns out that, well, what if there's defensive coding? Let's say they have a parameter, and really they want it to be non-null. But this is C++, so null could be passed in. So they have a code path which checks for null. And now they have a test, because they're actually being really responsible, that passes null to see what happens, make sure that the error path is properly handled. Well, now we have evidence that this code is nullable. We don't want evidence that it's nullable, because really their intent is that it's non-null. Okay, so what is the right annotation to choose? And ultimately, because of this can lead to a conflict. It can lead to, again, just being overly conservative. We basically ran analysis. What happens if we don't look at test code? If test code feels good because it'll give us the coverage, but any heavily used code is probably covered by the real uses, and that's probably enough, or maybe enough. What we basically did was we severed test code from the real code, from the production code. So test code still loops back to itself. We infer things about test code from other test code, but we keep them separate. We did see a slight drop in coverage, but we also saw about a 1/3 reduction in the conflict. So that's a really big deal. We went from 3% to 2%. Ideally, we'd find some way to split the difference, maybe with AI or something. We'll get back to that, but for now, that was ultimately, we think, led to a better outcome. Okay, so this is interesting. You have code which is using a pattern which ultimately we don't support or recommend. So this pattern comes up a lot for some reason, where you'll have two separate methods, has-foo and get-foo. It just seems redundant, to us. Maybe there's some attraction, but certainly for the analysis, everyone who just writes their own new class with these methods, we're not going to understand them. By default, we don't understand kind of the semantics of an arbitrary class. And so ideally, they'd write it as get-foo, now has the pointer, and then you check the pointer and use it. But if we're looking at the old pattern, we don't see that connection. Therefore, we're going to infer that get-foo internally, dereferences the pointer as if it's non-null, but then it's not protected. That's a conflict. So our options here are either to kind of simply normalize the code, translate all uses to what we call kind of the preferred pattern, or you can imagine that you allow the users to express it themselves. We're not going to do it. We can't build them all into our analysis, but you can imagine some sort of analysis, some sort of attribute which ties the two together. So we've done neither yet. At least we understand the problem, and kind of the resolution for now is that the way conflicts work is that we do not produce any annotation. We kind of hold those back. So that allows us, we still have, we're only 20% along the way. We have plenty of work to do, and we can come back to those and solve that in the meantime. Okay, so then there's also more interesting, situations. Again, you have a developer who wants to be conscientious. They don't want an uninitialized pointer. So the pointer is supposed to be non-null. It's supposed to be initialized, but maybe it's lazy init, or maybe it's a pattern like what I've seen shown here, where you immediately, you allocate it on the stack, say, and then immediately assign to it. So they indicate, they initialize it with null putter. That tells us the wrong thing. Or here's just, let's say, they actually put non-null. So here we have a conflict. We'll report that in analysis. The same idea could happen with abstraction, like you have a two-stage init, you have a constructor and then a init function. That we see even more commonly, instead of using some sort of factory pattern. So what do? Our sense is that really what you want is the users to not initialize, but to put some sort of attribute that says it requires explicit init. I know Clang has this. I don't know of other compilers, but it wouldn't surprise me if they do. And then they have the compiler enforce the initialization. So separate the two. Mark your pointer as you intend, and then check that it is properly initialized. Okay, and this one is fun. What happens if the annotation is correct, there's no conflict, but we're kind of suspicious that it's even right. Maybe they're being too conservative, they're building for the future, right? So here it's marked nullable, but we know that it's returning a non-null pointer. And this goes both ways. Again, it could be the analysis could detect this, or it could be an inference. We have to ask, should we infer non-null, because we're seeing clearly a non-null allocation there, and the developers say wants nullable. So this is like unknowable, right? There is no way this is exactly where the semantics of the code don't tell you the answer. Same idea comes up with, say, nullable parameters. But I think this is kind of one of the interesting kind of corners of this whole question. What is the actual API? And the API today, it says written, or the code today might not reflect with actual, evolution of the code, the desired evolution of the code. Here again, this could be these kind of small corner cases, something that AI could find hints that we can't, and try and resolve that in a way that's favorable. Okay, so just the next steps here are basically, we want to upstream of this. First is the Clang tidy. It's an open source, but we want to kind of get that out and in a way that's easy to use, so into the Clang repo. And then ideally you'd integrate it into the compiler itself. So it's not something separate, that you could actually put it just as a warning, and you don't allow code to compile. It breaks the build if it has a nullability warning. Internally, we've rolled out, we are aiming to finish rolling out nullable across the code base, where applicable. And then from there, we want to move on to actually the harder problem of changing the default so that a pointer in Google code would be a raw pointer. You just see a raw pointer would mean that it's non-null. For that, we need to decide how to handle that margin there of 15% really of cases in which there isn't a good answer as to what its annotation should be. Okay, so just kind of completing the picture here, I focus a lot on static, but static really isn't enough. That getting there takes time. Spatial safety, even if we have the answer, kind of migrating the code takes time. Temporal safety, we still need to work that out. And there are mistakes. What parts you choose to protect, or actual mistakes in migrating and the like. So we think it's actually important to complement all of this kind of static work with dynamic work. Address sanitizer, or ASAN, as was mentioned, is one approach that tends to be good for pre-production, for testing and the like, integration testing. But actually in production, we're seeing some other promising interventions, like control flow integrity, which is expensive but quite realistic for some applications. And I saw there's also a full talk on control flow integrity, which looks quite fun. So really interesting to see that become a realistic option in some cases. Heap partitioning, which is relatively new. Which basically says break up how you allocate memory, and that can avoid essentially cross-contamination between different kinds of objects, which can prevent, I can't get into it, but basically can prevent certain spatial and temporal safety problems. And finally, classic,
Question, is that mostly through TCmalloc?
Yes, through TCmalloc.
Yeah.
So it's very, very interesting. I just did not leave time in the talk to heap partitioning. And then finally, sandboxing. So there, that's classic. It's been around for probably decades at this point, and there's some new ideas there as well. But that is an important part of the toolbox. And then for reliability, UBSAN, say in Clang, that's undefined behavior sanitizer. That can be good to save nullability. Anywhere where we kind of statically, get it wrong, you can actually catch that dynamically. And there are more ideas, of the like. Okay, I promised in my abstract that I'd talk briefly about AI. I'm hoping to maybe say something new that you haven't already heard, but I'll make it just one slide. For what we're seeing in terms of trying to use AI for migration, the models are really good at local code understanding, shockingly good at static analysis. You can ask them, is there a temporal safety problem in this code or the like, and they actually can find a lot. The real challenge is not what they can do, it's getting them not to do too much. We see this time and again where they're just too aggressive. They might have come up with a really creative solution to the problem, but if you want to send out thousands and thousands of PRs, you want to make sure that the code owner is happy with them. Creative is not what we're looking for. Okay, so that's the kind of the key point. The other interesting point here is that you want to distinguish between first-party and third-party code. For first-party code, we're looking at the code owners. We want to make sure thure they'll be happy with the changes we make. It has to be maintainable code. But for third-party like traditionally, I mentioned earlier, often you just say we can't change third-party code. Or if you can, again, then you need to figure out how to upstream it, how to get kind of those changes integrated. You can't just kind of drop a huge amount of changes, fully upgrade a library. That's just not on the table. And maintaining downstream forks, at least for Google for the longest time, has been something we've actively avoided. Yes, there are certain points where we'll do downstream patches to third-party libraries, but mostly the philosophy is if there's a problem, we want to fix it upstream. But now, with AI, maybe merging is easier. So maybe we actually can keep downstream forks. And with this Vulnpocalypse coming, maybe it's a necessity. Maybe we need an ability to actually have all these downstream forks and maintain them and then just figure out later the problem of how you merge the code. Or if you make something that's really dependable, you can, every time you import, you apply the changes, you harden, migrate, and do all the improvements to the code, and throw it away on the next time. The key thing then becomes how do you validate the code? It's not maintainable code, it's about validatable code. You need to be sure that in fact the code that you've now generated, that you've changed, is the same or same enough as the code was before. And finally, just insight here is that what we're seeing is that it's actually quite, what seems most promising is not to replace all of our classic techniques with LLMs. Not just because they're non-deterministic, but they're at least now really expensive, but some sort of hybrid solutions. Where, say, an analysis will mark up the code and then pass that to the AI, and the AI can do much better now with all those hints, for example. Or there are areas which the AI just can do things that it's really, really hard to write good rule-based analysis for, like choosing a good variable name. This is something we've always punted on. And AIs are really good at it. So do most of the work yourself and then pass it to the AI and then make sure the only thing it's changing is your variable names, or structure the problem so the only thing it can change is the variable names. But anyway, but we're seeing definitely a future for these to work hand in hand. Okay, so let me just finish up. From where I'm standing, and I don't know if you folks have the same experience. Life today just feels like quicksand. So the software engineering, everything I've learned and I've experienced feels like it's being challenged and constantly changed because of where the frontier models are going. And with all that, what I also see is that foundations still matter. We still need to get to a well-defined, safer subset, or safe, ideally, subset of C++, both for humans for all the reasons that have always been the case, and also even, for AI. If you want, again, an AI to agentically migrate your code, you need some deterministic gatekeeper, which will tell the AI, when it fails, so it can keep trying and do it right. And overall, kind of the lesson, I'll take this old expression, I think it's from like the 60s or something, but it's hard to actually find where it came from. The best time to plant a tree was 20 years ago. Second best time is now. Maybe game over for us. Maybe the Vulnpocalypse is just going to wash us all away. I don't think so. I think it's worth continuing to invest. It would have been nice if we had done this 20 years ago, but let's try and make this happen now. Thank you. Any final questions? Yeah.
Your analyzer that tries to automatically determine whether pointers are nullable or non-nullable,
Yeah.
and incidentally finds a bunch of conflicts, which are bugs.
Some of which are bugs. Some of which
Right.
are limitations. Yeah.
Right. You said it uses duck typing to determine what pointers are. Does that mean that it also picks up optionals so that it can find optionals that are accessed when they might not be valid? It's
Yeah,
the same, it's basically the same thing in a sense.
Yeah, so there's actually more history there. So maybe we don't use duck typing. I can't remember. Optional we definitely don't pick up because the history of the nullability analysis was that originally it started with an optional and status or analysis. And then we said, oh, this was so successful, let's move into nullability where there's new challenges. So we do have the same core technology is shared between them. The optional one is easier because it's explicit, right? Enter optional int. So the answer is nullability analysis doesn't do that, but the same underlying, it's called the Clang data flow framework, and the same ideas kind of inform the two of them. So it is available. That already is upstream. You can just use that now from Clang.
So these tools are in Clang compiler, but not Clang tidy?
No, these are in Clang tidy and not the compiler.
Okay.
Yeah, because of the precision of the analysis, in order to achieve the precision of the analysis, we use a SAT solver. We kind of track. basically use a logic to track everything we're seeing as we flow through the code. Stat solvers are expensive, and we have not, I think you have to optimize that or cut down on your precision. So we definitely have tested cutting down on precision, a much simpler Boolean model, and that's faster, but it's you pay for it. It's probably good enough that you could integrate into the compiler, and kind of it's just a more conservative analysis. Ideally, we'd find a way to optimize calls to stat solvers so there are fewer of them, and that's possible as well. Yes.
Do you have bugs because of improper use of moving, that things are moved out and then still used?
You mean like, say, temporal safety?
Is this something that happens in your code?
Yeah, I mean, we've seen that. So the lifetime safety analysis does take into account the semantics of move.
Yeah, but move out is not really lifetime. It is similar, but not.
Yeah, it's more obviously you have to know that like when it's moved, that the fact that the aliasing, you have to get the aliasing correct. So you want to understand moves and then track the aliasing so that it can make sure that there are no bugs. There is usually after move analysis already in Clang tidy. So we have that turned on in general. That's going to be more conservative, but that's quite effective in catching those kinds of errors.
Yeah, so coming back on the optional, the hardened standard library will detect the optional cases already, right? So you at least have that runtime backup. I wanted to ask you about something in the first section. You mentioned a bounded iterator proposal. Was that like a Clang thing, or because I went looking for it and I didn't find it? So
Yeah, it's not. I don't think it's a Google thing. I forget exactly. So I thought that was. Yeah, it could be it's Clang. What?
Chipmunk.
Well, literally, yes, literally. Yeah, I can look that up and find that for you. But I thought that was a more standard thing. There's someone else in the project who was working on that aspect, so I forget exactly the details there.
well, if there isn't, I'd be interested in helping.
Oh, sure, yeah, let's talk. I'll find that.
Yeah.
Anything else? Okay, can we wrap up a few minutes early? Thank you.